Imagine stepping into a time machine and setting the dial back to billion years. The Earth you're about to land on is both alien and strangely familiar. It's roughly halfway through its lifespan, but the world looks nothing like the one we know today. As your ship descends, you don't see lush forests, towering mountains, or roaming animals. Instead, you're greeted by a barren, rocky landscape, interrupted only by shallow seas. The continents are unrecognizable fragmented landmasses scattered across a world still in the making. There's no grass beneath your feet, no trees to give shade, not even a single flower. This is an Earth before plants, before animals, before complexity. Life does exist here, but it's almost invisible to the naked eye. The planet is ruled entirely by microorganisms, and although they might look insignificant, they're about to rewrite the destiny of our planet. Before you step outside, you'll need an oxygen tank. Not because oxygen is absent it's here, but it's nowhere near enough for you to breathe safely. In fact, Earth's oxygen levels are less than 10% of what they are today. The atmosphere is instead packed with carbon dioxide, methane, and water vapor, a cocktail of gases that shaped the early climate. Now, turn your eyes to the oceans. At first glance, the waters seem lifeless, but they are teeming with slimy green mats of cyanobacteria. These tiny organisms don't look like much, yet they're among the most influential life forms to have ever existed. Why? Because they know a secret trick: photosynthesis. By harnessing sunlight, they can split water molecules and release oxygen as waste. It might not sound dramatic, but this ability will trigger the Great Oxidation Event, a planetary upheaval that wiped out most of Earth's early life. Paradoxically, the same oxygen that allows us to live today was once the deadliest poison for almost all the organisms on Earth. This invisible war between oxygen-producing bacteria and the life forms that couldn't tolerate it was one of the first mass extinction events in Earth's history, and it set the stage for the complex world that would eventually emerge. But this is just the beginning. To truly understand the scale of this transformation, we need to journey even further back in time to see how it all started. To understand how oxygen became both a savior and a killer, let's rewind even further, about 2.5 billion years ago. Back then, Earth's atmosphere had zero oxygen. It was dominated by methane and carbon dioxide, creating a greenhouse effect that kept the young planet warm and stable. The oceans were alive with simple microbes, but one species of bacteria, cyanobacteria, changed the rules forever. These organisms evolved the ability to use water and sunlight to generate energy, releasing oxygen as a byproduct. At first, the oxygen quickly reacted with minerals like iron, disappearing from the environment before it could accumulate. But as cyanobacteria multiplied, their oxygen output began to overwhelm the planet's chemistry. For the first time in history, oxygen started to build up in the atmosphere. To us, this sounds like progress, but for most of the bacteria that had thrived in oxygen-free waters, it was a death sentence. Oxygen was toxic, it damaged their cells and destroyed their way of life. Entire ecosystems collapsed. In fact, scientists estimate that up to 99% of early microbial species vanished during this event. This catastrophe is known as the Great Oxidation Event, one of the most important turning points in Earth's history. It was both a tragedy and a breakthrough, killing off countless species, yet laying the foundation for the complex life that would follow billions of years later. But oxygen didn't just poison microbes, it also disrupted the climate. By reacting with methane, a powerful greenhouse gas, oxygen removed one of the key ingredients keeping Earth warm. With methane gone, global temperatures plummeted. The result? Earth plunged into its first major ice age, the Huronian glaciation. For nearly 200 million years, massive sheets of ice covered the planet, from the poles to the equator. Oceans froze. Land turned white. The world became a snowball drifting through space. Life clung to survival in tiny, hidden refuges. Just 1% of microorganisms managed to endure the freezing hellscape. These survivors would one day give rise to everything we see today: plants, animals, and eventually us. The Great Oxidation was a paradox, a catastrophe for early life, but the spark of opportunity for evolution's grand future. And when the ice finally began to retreat, Earth was ready for its next transformation. For nearly 200 million years, Earth was locked in a deep freeze. Ice stretched across continents, oceans turned to slush, and sunlight bounced off a planet wrapped in white. It seemed like life's fragile spark would be snuffed out forever. But beneath the frozen crust, the planet was far from quiet. Deep inside Earth, molten magma churned restlessly and cracked. unleashing massive volcanic eruptions. For millions of years, these volcanoes pumped carbon dioxide and water vapor into the air gases that trapped heat and slowly began to thaw the icy grip of the Huronian glaciation. At the same time, the sun was growing brighter. Every 100 million years, its luminosity increases slightly, and by now it was a few degrees warmer than before. The combined effect of volcanic greenhouse gases and a stronger sun tipped the balance. Ice sheets started to melt, oceans flowed freely again, and the climate warmed. But nature had one more surprise waiting. In what is now Gabon, Africa, a unique geological accident occurred. The world's first natural nuclear reactor. Rich deposits of uranium, concentrated over billions of years, reached a critical mass. Without any human technology, nuclear fission began splitting atoms, releasing neutrons, and generating heat. This reactor operated naturally for hundreds of thousands of years, further contributing energy to the planet's dynamic system. As the ice retreated, Earth underwent a dramatic makeover. Volcanic activity fused scattered landmasses into one of the earliest supercontinents, Nuna. Over time, Nuna's shifting plates would carve mountains, form oceans, and set the stage for future continents. Meanwhile, life itself was stirring. The small fraction of microbes that survived the oxygen-rich environment. Some learned to use oxygen to burn food more efficiently, creating the first steps toward complex metabolism. Cyanobacteria continued photosynthesizing, releasing even more oxygen into the skies. For the first time, Earth's atmosphere began to resemble the one we depend on today. And as oxygen accumulated, it formed a protective ozone layer, shielding life from deadly ultraviolet radiation. This invisible shield expanded the habitats where organisms could survive and evolve. The frozen prison was broken, the planet was warming, and life was preparing for its next great leap. But what came next would change biology forever: the dawn of complex, multicellular organisms. With Earth thawed from its icy prison, a new chapter began. The atmosphere was filling with oxygen, the ozone layer was forming overhead, and the oceans were alive with microbial survivors. But something extraordinary was about to happen. Cells were evolving beyond simplicity. For nearly 2 billion years, life had been nothing more than single-celled organisms, tiny, efficient, but limited. Now, under the pressure of survival in an oxygen-rich world, some cells developed a nucleus, a protective chamber for their DNA. These were the first eukaryotic cells, and they changed everything. The nucleus wasn't their only innovation. These cells also contained specialized structures, mitochondria, that allowed them to process far more energy from food than any microbe extract them. Energy meant growth. Growth meant complexity. Over time, eukaryotic cells began to cooperate. Instead of living alone, they stuck together, forming colonies where individual cells specialized in different tasks. This was the birth of multicellular organisms. Imagine microscopic clusters of cells dividing labor, some focusing on movement, others on feeding, others on reproduction. Though still tiny, these early multicellular creatures represented a radical leap forward. They were no longer just survival machines, they were evolving into systems. Fossil evidence shows that some of these organisms reached sizes up to 17 centimeters, soft-bodied pioneers of a new biological frontier. Oxygen played a crucial role in this transformation. With more oxygen available, cells could sustain larger bodies and more complex interactions. And thanks to the newly formed ozone layer, they could survive closer to the surface, exposed to sunlight, without being destroyed by ultraviolet radiation. This was the blueprint for all future life: plants, fungi, animals, and eventually humans. Every tree in a forest, every bird in the sky, and every person walking on Earth today can trace their origins back to these first experiments in multicellularity. Yet evolution is never smooth. Many of these early pioneers vanished without leaving descendants, but their legacy lived on in the cellular architecture of everything that followed. The Earth was now alive in a new way. From microscopic mats of cyanobacteria to colonies of eukaryotic cells, life was preparing to fill oceans, continents, and skies. The stage was set for an explosion of diversity that would reshape the planet forever. For billions of years, Earth's oceans were home to simple microbes and small colonies of multicellular organisms. The seas were quiet, dominated by soft-bodied life that left little trace behind. But then, around 541 million years ago, something extraordinary happened. Life suddenly exploded in diversity and complexity. This event is known as the Cambrian Explosion, and it marks one of the most important turning points in biological history. Within a geologically brief span of time, just a few tens of millions of years, nearly all major groups of animals appeared in the fossil record. Creatures with shells, skeletons, eyes, and complex body plans surged into existence, transforming the oceans forever. Why did this happen? Scientists believe several factors aligned. Oxygen levels in the atmosphere and oceans had risen high enough to support larger, more active animals. The ozone layer provided better protection from deadly radiation, allowing life to thrive closer to the surface. New ecological interactions, predators and prey, ignited an evolutionary arms race, driving rapid innovation in body forms and survival strategies. In the seas of the Cambrian, strange and alien-looking creatures thrived. Some were armored like living tanks, others had spiny limbs or bizarre appendages for grabbing food. The first arthropods, ancestors of insects, spiders, and crabs, crawled across the seafloor. Early mollusks and primitive fish-like animals began to appear. Even the first chordates, distant relatives of humans, made their debut. This explosion of biodiversity not only filled the oceans with life but also laid the foundation for every ecosystem that followed. The food chains of today, predators, grazers, scavengers, all trace their origins back to this ancient revolution. The Cambrian seas were a world of experimentation. Many species thrived, but many more disappeared, leaving only fossils as evidence of their brief existence. Yet every failure was part of a larger success, evolution testing countless designs until the strongest endured. For the first time, Earth was not just inhabited, it was teeming with complex life. The oceans had become laboratories of innovation, where evolution worked at breathtaking speed. But the story of life is never steady. Just as quickly as it flourished, life would soon face devastating trials. Earth's history is marked not only by creation but also by destruction. Life on Earth has always been resilient, but it has never been safe. Across deep time, our planet has faced waves of destruction so powerful that they nearly erased life itself. These cataclysms are known as mass extinctions, moments when entire ecosystems collapsed and most species vanished forever. The first great extinction struck more than 440 million years ago, when dramatic climate shifts froze the seas and then warmed them again. Countless marine creatures disappeared, reshaping ocean life. Later, volcanic eruptions poisoned the atmosphere, superheating the planet and starving the seas of oxygen. But the most devastating of all was the Great Dying, around 252 million years ago. During this event, over 90% of all species on Earth were wiped out. Oceans turned acidic, skies choked with toxic gases, and even forests burned to ash. For a moment, it seemed as though life's story had reached its final chapter. And yet it didn't. From the ruins, survivors adapted, evolved, and began again. The ancestors of dinosaurs, mammals, and eventually humans emerged in the wake of catastrophe. These cycles of destruction and renewal remind us of a profound truth. Extinction clears the way for new beginnings. Without the Great Dying, there might never have been dinosaurs or us. Earth's history is not a straight line of progress but a rhythm of creation, collapse, and rebirth. Our world today, its forests, reefs, and skies exists only because life has endured every trial the planet has thrown at it. This is the legacy of Earth, a world forged through fire, ice, and endless renewal. If you enjoyed this journey through deep time, make sure to like, share, and subscribe to BrightBoundX for more explorations of Earth's past, the mysteries of the universe, and the story of life itself. Together, let's uncover the secrets that shaped our world and the possibilities that lie ahead.